Okay, so let's scoot on to the new topic, real zeros of a polynomial function. I have two definitions for you, or two theorems for you, that really go hand in hand with each other. Let's look at this first one. Let f be a polynomial function if f of x is divided by x minus c, then f of c is actually the remainder. So here's the deal. This theorem is giving you another way of finding the remainder. Instead of doing your division, instead of doing your long division, putting your polynomial here, your x minus c there, and doing your long division to see about a remainder, this polynomial, or this theorem, is giving you another way to find it. Now here's what I need you to understand. They divided by x minus c, didn't they? But notice what they plugged in? Yeah, they plugged in a positive c. You're like, well, how'd they do that? They took what you were dividing by, set it equal to 0, and solved for x. This is why you are plugging in, instead of plugging or leaving the x, you are plugging in c. This is how you get the c, by setting x minus c equal to 0. Good? Now, this next theorem goes hand in hand with the remainder theorem. Here's what I need you to think about. If you do this division, this long division, or you take x minus c equal to 0 and then plug this c into the polynomial, if this is supposed to divide evenly, then your remainder should be what number? Yeah, your remainder should be 0, right? If your remainder is 0, that means this x minus c divided into the polynomial evenly, right? That means when you plug c into here, you should get a 0, shouldn't you? Well, the factor theorem says, let f be a polynomial function. X minus c is a factor of the function. This means if and only if. X minus c is actually a factor of the function if and only if f of c equals 0. These two theorems go hand in hand. This first one shows you how to find the remainder a different way other than long division. This theorem says if that remainder happens to be 0, then x minus c is a factor. Cool? Okay, so hang in there. I'm going to get us some examples. Okay, so let's look at the directions. They ask us to use the remainder theorem to find the remainder, and then use the factor theorem to determine if x minus c is actually a factor. So let's look at number 1. They give us this third degree polynomial. They give us x minus 2, and they'd like us to use the remainder theorem first to find a remainder. So what do we need to do first? Good. We need to take x minus 2, set it equal to 0, and solve for x, which in this case x equals 2, yes? And then the remainder theorem says now you're going to plug in that 2 to the polynomial. So I am going to take 2 seconds, well maybe 3, to write this out. It's always a good idea to do that. And see, I wrote an x by mistake. So let me get rid of that x and let me put the 2 in its place. And I know some of you have your calculators out. You use your calculator, I use my calculator. And yes, I'm writing all the steps out because eventually people will go, wait, where'd you get these numbers? So I got f of 2 equaled 8. Did you get that remainder? Good. So now, the factor theorem. Based on my remainder, is x minus 2 a factor of this third degree polynomial? Correct. The answer in this case is no. Because you got a remainder of 8, not 0. Cool? Okay, so let's look at this other one, the second example. They give me a fourth degree polynomial. They give me this factor, and they say use the remainder theorem to find the remainder. So what do we have to do? Yep, we have to set this equal to 0 and solve, so I get x equals 1/2. And some of you are like, are you kidding me? We're plugging in a fraction? Yes, we are. It's not so bad, trust me. All right, so f of 1/2, and I know for sure that you guys have those calculators out. Okay, you use your calculator. I'll use mine. And I'm running a little bit out of board space, so hopefully you see that. So let's see. Well, 1/8 minus 1/8, 0. Positive 1 minus 1, 0. So it looks like I get 0 here. So it looks like f of 1/2 is actually, if I have a little bit more room down here, yay, I do, I can write it. Looks like f of 1/2 equaled 0. So, is x minus 1/2 a factor of this 4th degree polynomial? Yes, it is. By the factor theorem, that's a huge yes. Cool? All right, loving it. Hang in there. Got another theorem for us to work on. Okay, so let's move on to the next theorem, known as the intermediate value theorem. Let f denote a continuous function. If a is less than b, and f of a and f of b are opposite signs, then f has at least one 0 between a and b. So, we read it through once. Let's go back and do some picking apart and see what information it really tells us. F is a continuous function. What does continuous mean? It means there's no break in it. You can just trace it with your pencil, pen, crayon, whatever you want to do, and there's no break in it whatsoever. You never have to pick up your pencil and put it somewhere else to continue the graph. Okay? If a is less than b, so clearly I have two different numbers, one larger than the other, and f of a and f of b are opposite signs. So if they're opposite signs, one is good, positive, and the other one is good, negative. So here's what I need you to understand, though. I need you to understand what f of a and f of b actually represent. So we know what f of x means, right? F of x replaced the y. So f of x is y, isn't it? So here's the deal then. When they say f of a, that is that's right, f of a is a y value. It is a y value when you plug in a. And f of b is also a y value when you plug in b. Got it? F of a is a y value when you plug in a. F of b is also a y value, but when you plug in b. So question, what do a and b represent? Good. A and b actually represent x's. Here's first x, here's the second x. Are you with me? And f of a and f of b are those y values that go with those x's. Cool? Okay. Then it says, if they are of opposite signs, then f, the function, has at least one 0. Remember, 0 is another word for a solution. One solution between a and b. So here's the deal. Let's put it into practice. Here's a function they've given us, a 4th degree polynomial, and they're wanting to know if there is a 0 on this interval. Well, if they want to know if there's a 0 on this interval, that means -1 and 0 are representing, yep, these are your x's. There's your first x, there's your second x. And in order to decide if there is a real 0 in between these two x's, I need to find their y values. Because when I find their y values, and if they're opposite signs, then we're good to go. So, let's find their y values. So let's find f of -1. So remember, I take about 2 seconds, 3 seconds. I fill in what this is supposed to look like with that number, and then I work it out. right? That's going to be positive. That's going to be negative times a positive 8. That's going to be positive, but with the negative on the outside. Agreed? Negative 7, negative 8, negative 6. So I have f of negative 1 being a negative 6. Hopefully you got the same. Okay, so now let's figure out f of 0. Clearly this one's going to be a little bit easier. I don't even need to plug it in. What do we get? Yeah, we get 2. So the deal is, are these of opposite signs? Is f of negative 1 and f of 0 opposite signs? And yes, they are. So is there at least one 0 between negative 1 and 0? Yes. So there is at least one 0 on this interval. Cool? Okay, so you're going to need your graphing calculators out so I can show you how. Okay, so let's look at finding the 0 for this particular problem. Remember, we had used the intermediate value theorem, and it told us that there was a 0 in between the negative 1 and the 0 for this particular fourth degree polynomial. So we need to go graph it and find it. First, we need to input it. So y equals, right? By the way, please make sure all your plots are off. If they're not, go in, turn them off, because if they're on, we're going to have a situation in terms of your graphing. And now I'm going to type in x to the power of 4 plus 8 x to the power of 3 minus, remember, hit the minus key, not the negative key, x squared, and then finally plus 2. Okay, now I am actually looking for my x's between negative 1 and 0. So I'm going to go to my window and see what it's set at. It's set at negative 10 for the x min and positive 10 on the x max. You know, those are fine, but they're a little bit too wide, shall I say? So I'm just going to go from negative 3, and then I think I'll go to positive 3. I'm just going to make the x window shorter, and then I'm going to go to the graph. Okay, so I'm noticing between negative 1 and 0 that this graph is truly crossing the x-axis, and you see it as well as I do. Now I've got to find what that value is. So here's how we do it. And again, I'm hoping you're taking notes. So we have to hit the second function and go to trace, which actually above trace was that calc word. And I need to find a 0. So on my screen, it's option number 2. So I'm going to click on number 2. And now notice it's telling me at the top the equation that my blinking dot is on. At the bottom, it's asking me for a left bound, and it's telling me where my blinking dot is located. My blinking dot is on the y-intercept. That's great. I'm not looking for the y-intercept. I'm looking for the x-intercept. And it's asking for the left bound, which means I need my blinking dot to the left of this x-intercept. And to the left of it, in this case, will be below it. So I want to be as below it as I can, but as close to underneath it as I can be. And that looks about right. And I'm going to hit enter. And notice it asks me for a right bound. So now I need my blinking dot to the right of that x-intercept. And to the right of it, in this case, is above it. So I want to get just above it, not by much. And I can see that a y value is positive, so we're good. See the point underneath? So that y value is just above the x-axis. And then it's going to say, well, do you want me to take a guess? And I'm going to say, yes, take a guess. And by hitting enter. And it's computing, and it's telling me that my 0 for the x is negative negative 0.604, etc. And notice the y equals 0. So in this particular case, if they ask, and they asked us to round to 2 decimal places, if they ask us to do that, you are telling me that my x in this case is equal to negative 0.60. Cool? Okay, so you have fun with this, and we're moving on. Okay, so let's look at this next theorem. It's called the rational zero theorem. Now you need to remember what the word rational means. Rational is a fancy name for a fraction. So here we go. Let's look at the theorem. Let f be a polynomial function of degree 1 or higher where, here's our typical polynomial. We have seen it before. This is nothing new. Where each coefficient is an integer. Remember, sometimes it's easier to describe what's not an integer. Right. An integer is not a fraction or decimal. Now, if P over Q is a rational zero, so let me stop a second. Rational means it's a fraction. Zero means it's a solution. So we have a solution that looks like a fraction, right? By the way, remember, 5 is also a fraction. 5 over 1, right? Okay, so if P over Q is a rational zero of f, then P is a factor of the constant and Q is a factor of the lead coefficient. So let's take a look at this particular polynomial, okay? And they didn't give me any place to start looking for possible solutions to this polynomial. I know I'm supposed to have 4 answers because it's to the power of 4. Got it? Okay. This theorem helps me find possible solutions for polynomials with no starting point. Understand that. This polynomial, or I should say this theorem helps me find possible solutions for any polynomial when they didn't give me a starting point. So considering they gave me this 4th degree polynomial, if they asked me to solve it, I'm like, well, how do I solve it? There's no starting point. This is where I use this theorem. So first thing I need to do, because they said if P over Q is a rational zero, well, I need to identify P and I need to identify Q. P is the factor of the constant. Well, what's my constant here? Yeah, 9. Now, I like to use the sandwich technique. The first number that goes into 9 is 1. That's right. I know some of you said a different number, but it's 1. 1 goes in there 9 times, doesn't it? By the way, it could be a positive 1 or a negative 1, which means it could be a positive 9 or a negative 9. And then after 1 is, 2 doesn't go in, but 3 does. And that's where I sandwiched, because there's nothing left between 3 and 9 to try. Okay, Q is a factor of the lead coefficient. Well, what's my lead coefficient? It's 6. So, first number that goes in, 1 and 6, right? Could be positive or negative. After 1 is 2, and it goes in there 3 times. And there's nothing between 2 and 3 for me to try. Good? Okay, so now to find my possible solutions, which means every P value goes over every Q value. So watch. I'm going to take this 1 for the P's and I'm going to place it over every Q. So 1 divided by 1, that's 1, plus or minus. 1 over 2, yes, we get fractions. 1 over 3, and 1 over 6. Now that I'm done with 1, I'm going to go to the 3. So 3 over 1, right? 3 over 2. 3 over 3. What's 3 over 3? Yeah, that's 1. I already have 1. I'm not going to write it again. 3 over 6. That's a half. I'm not going to write it again. I already got it. So the 3 is done. Look at the 9. Yep, 9 over 1. 9 over 2. 9 over 3 is, 9 over 3 is 3, which we already have. 9 over 6, that reduces to 3 halves, which we already have also. So here's the deal. these are my possible solutions for this fourth degree polynomial. How many solutions am I supposed to have for this fourth degree? 4 of them. How many possible ones do you have? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Not 8, they're plus and minus. I have 16 possibilities. Are you kidding? I have 16 possible solutions for a polynomial that only needs 4 answers. Yikes! Now what do I do? Hang in there. We're actually going to work on some examples and I'll show you what. Okay, so let's look at this problem they're asking me to solve. Now, I'm supposed to come up with 3 answers, correct? Now, when we learned factoring way back when we had 4 terms, we could group them together. Now, if I look at trying to group these, I notice it's not going to happen. Because after I factor out something from the first 2 terms and something from the last 2 terms, what's left over won't be the same. So factoring isn't going to help me with this, which means I'm going to need to find some kind of starting point to help me solve this. That's where the rational zero theorem comes in. It helps me find the possibilities. Got it? The possibilities. So, I need some possibilities to get started. Remember those P's and Q's? All right, so my P is the 12, right? Because that's the constant. So, that's right, 1 goes in there first and it goes in there 12 times. 2 goes in there, it goes in there 6 times. Notice how I'm sandwiching. After 2 is 3 and it goes in there 4 times. And that just about does it. Q, well that's just the number 2, so that's easy enough. Cool? Okay, now I need my P's over Q's because my P over Q's, these are my possibilities. By the way, that was the number 2. Okay. So P over Q, these are my possibilities. So remember, every P goes over each Q. So let's start writing it. So 1 over 1, 1 over 2, done with the 1, 2 over 1, 2 over 2, well that's just 1, so I don't have to worry about it. 3 over 1, 3 over 2, 4 over 1, 4 over 2, well that's just 2, don't need it again. 6 over 1, 6 over 2, well that's 3, already got it. 12 over 1, and 12 over 2, well that's 6, already got it. So let's see, what do we have in this case? 3, 6, 8, I got, again, 16 possibilities. Well, I only need 3 answers. Lovely. Okay, so now, some of you know how to do this next process that I'm going to show you, and some of you may not be so sure. What I'm going to do to help me figure out very quickly which of these will be solutions is something called synthetic division. Here's why I'm using that. I could use the remainder and the factor theorem. I could take all 16 of these, plug them into the original polynomial, and hopefully I end up with 0. Because if I end up with 0, that means the remainder is 0, which means that number goes in there, right? But you know as well as I do, not all my solutions are nice and perfect. Sometimes I get a square root answer, which I don't see any square root possibilities here, so there's no way you're going to come up with a square root answer or find it just by plugging these numbers in. Sometimes you come up with imaginary answers. Yeah, I don't see any imaginary answers here either. So the remainder and the factor theorem are both very good theorems. However, when I'm trying to solve, it's not the best combination for me to use because I won't get square root answers and I won't get imaginary answers. With me? Okay, this is why I prefer synthetic division. So, this is your setup. Especially for those who are not certain of synthetic division or have never used it, this is your setup. Down here is the answer. Out here is where you write your dividing by, like what you're dividing it in, or you're taking this number and dividing it into here. Now, synthetic division doesn't care about variables. It only cares about the coefficients. So, in this particular case, all I'm going to do is write down my coefficients. So, by the way, make sure descending order, right? So we have 2, -5, -4, and 12. Are you with me? Now, I need you to understand something about synthetic division. Synthetic division actually reads these numbers from right to left. So it reads this as the constant. It reads this as the first power, second power, third power, which is awesome. But if it's missing a power, we must put in a 0. Remember the last problem I wrote on the board? We had 6x to the 4th minus x squared plus 9. If you needed to set that up with synthetic division, then you better have written 9 for the constant, 0 for the power of 1, -1 for the power of 2, 0 for the power of 3, and 6 for the power of 4. This is what you would have need to have written if you were going to use synthetic division. You needed to put these zeros in for the missing third and first powers. Cool? Okay, now, synthetic division. I got 16 possibilities over here. You're like, where do I start? Well, I start anywhere I feel like starting. I'm going to tell you though, I usually don't try the larger numbers like the 6 and the 12. I probably wouldn't try those because those usually don't work. They do sometimes, but not always. And I know some other numbers you guys are saying I'm not going to use. You aren't going to use fractions. Well, guess what? I'm going to pick a fraction because I'm going to show you if a fraction works, how easily it does work. Okay? So, let's see. I'm going to pick 1/2. And I'm going to pick, I think I'm going to pick a positive 1/2, okay? Because I could pick the negative, but I think I'm going to go with the positive 1/2. Now, synthetic division always starts the same way. This first number always comes down. Always. I don't care what it is. It always comes down. And then I get to do, remember, this is division. So when you put a number in the answer spot, you multiply by what's on the outside, don't you? So 2 times 1/2, that's 1. And I put it under my next number in line. And all I do is I combine these. I don't have to worry about subtracting or adding. I combine these numbers. A -5 and a positive 1 gives me a -4. And then I start over again. I take my number in the answer spot. I multiply by what's on the outside, which will give me, good, -2, which gives me -6. Actually, so far so good. Why? Because I'm not getting any fractions here. If a fraction doesn't work, you end up with a whole bunch of fractions, which means that was the wrong number. Got it? If a fraction works, I never end up with fractions, which here it's looking really good because I'm not ending up with fractions. Okay, -6 times 1/2 is -3, isn't it? And that gives me a positive 9, doesn't it? Here's what you need to understand. This last number is the remainder. And the 1/2, it was working beautifully, right? But it didn't work. I ended up with a remainder of 9. I don't want a remainder of 9. I want a 0 remainder. So the 1/2, the positive 1/2, doesn't work. Nixing that out. So guess what? Gratefully, I have a light board here, so it's going to be easy for me to erase. And you might want to get yourself maybe a personal whiteboard so you can do this, but time for me to erase these numbers and try again. All right? Okay, so you guys think, what do you want to try next? The positive 1/2 didn't work. Oh, I hear some of you go, well, -1/2. Okay, well, we can try the -1/2 while we're here. Why not? Let's see what happens, right? It's all right. The smudges will go away here in a moment. All right, so you want to try a negative 1/2? Let's try it. Why not? Maybe it'll actually work. So, again, I start by bringing that 2 down. So what's 2 times negative 1/2? Good, negative 1. I combine them. Excellent, negative 6. And then I do the negative 6 times the negative 1/2. Yes, positive 3. Right? Which gives me negative 1. And I multiply those and I get a positive 1/2, which I don't even have to add. I know is not going to work because I ended up with a fraction. So forget that one. Okay, so 1/2 is not working at all. So we need to try another number. What do you guys want to try? 1/2 didn't work. Negative 1/2 didn't work. What do you guys want to try? Some of you are saying try 1. I hear some of you saying try 3. Okay. Some are still saying try 2. Well, you know, here's the deal with this. That's the deal. This is like almost a little bit of a trial and error. So, how about, let's try that 2. I heard some of you say 2. All right, so 2 times 2. Good. 4. That gives me negative 1, right? That gives me negative 2. That gives me negative 6. That gives me negative 12. That gives me 0. Yay! We found one of the solutions. One of my solutions is x equaling 2. Awesome. So let's see. I'm going to write it over here. And I have how many more solutions to try, or to get? I have 2 more solutions. Now here's the deal. You can go back, erase this 2, and plug in the other numbers to see if they work. Remember though, sometimes you could get answers that have square roots in them. Sometimes you could have answers that have i's in them. Here's my recommendation. Is division a building up process or cutting down? Good, it cuts things down. So I had a 3rd degree equation, right? I divided it by this 2, and remember your factor and remainder theorems, right? Since x equals 2, then I have a factor of x minus 2, don't I? This is a power of 1, isn't it? You have a 3rd degree, you divide it by a 1st degree. This is what degree polynomial? It's a 2nd degree. Do you know how to solve a 2nd degree equation? Yeah, you do. You can either factor that thing or you can use the quadratic formula. Whatever floats your boat. Are you with me? Let's work smart, not hard. Right now I know that this is a 2nd degree polynomial because this one was a 3rd. You divided it by a 1st. And now you're left with a 2nd degree. So, I am going to take my 2x squared minus x minus 6. And by the way, you are setting it equal to 0 because you're solving this, right? And I'm either going to factor it or use the quadratic formula. Me personally, I'm going to factor because I think it'll factor. Some of you are using the quadratic formula, that's fine. Use the formula. We'll come up with the same solutions. Okay, so I end up with x equaling a negative 3/2 and x equaling a positive 2. Oh wow, look, 2 was an answer again, wasn't it? It became an answer twice, didn't it? So be it. If that's the way it works, that's the way it works. So, my other 2 answers are x equaling 2 and x equaling negative 3/2, which means I have 2 other factors, and here they are. Y'all with me? Okay, so let me go get another problem so we can work on it some more, all right? But let's do a brief recap. I had a 3rd degree polynomial that they wanted me to solve. This would not factor, which means I had to go find myself some kind of starting point. in order to figure out what numbers might work. Because there are oodles of numbers. There's millions, billions, trillions of numbers out there. Gratefully, we narrowed it down to 16 numbers that were possibilities. And instead of using the remainder and factor theorem, because they won't give me square roots and imaginary numbers as answers, we chose to use synthetic division, because synthetic division took my third degree, cut it down to a second degree, and the second degree polynomial, when I factored or use the quadratic formula, this is where my square roots will come from if they're answers. These are where my eyes will pop up if they're supposed to be answers. Are you with me? Okay, so hang in there. I'm going to get us another. Okay, so let's look at this next problem. They're still asking me to solve, and in this case, they were very nice. They set it equal to 0 for us to let us know to solve. And they didn't give me a starting point. Now here's the deal. That means I'm going to go use the rational zero theorem. However, one of the key requirements of that theorem was that your coefficients had to be integers, which means they couldn't be fractions and they couldn't be decimals. Do you notice I got fractions here? Well, that's not going to work for us. So you know what we're going to have to do? Right, get rid of the fractions. And how do I get rid of the fractions? Yeah, I'm going to have to multiply, in this case, both sides by 3. So, when I multiply the entire equation by 3, I end up with 3x cubed plus 4x squared minus 7x plus 2 equaling 0. This is the equation that I need to solve. Got it? Okay. So again, they didn't give me a starting point. I need to come up with one, which means we need to find, excellent, our P over Q's, or P's and Q's, shall I say. So let's deal with the P first. What do I look at? Good. I look at the 2, the constant, which means the only factors of 2 are 1 and 2, both positive and negative. And for Q, yeah, that's the lead coefficient, which in this case is 3. And again, I only got 2 numbers. There it is. Okay. So, your P over Q's. Ready? So, it's either plus and minus 1, and then plus and minus 1 over 3, correct? So I'm done with this guy. 2 is next, so 2 over 1. So plus or minus 2. And plus and minus 2/3. So I have 8 possible answers here, but I only need 3. And there's no guarantee all 3 of them are in those 8 possibilities. Some of my answers may involve square roots. Some of my answers may involve imaginary numbers. So here's the deal. The remainder and factor theorem are not going to give me square roots, and they're not going to tell me about imaginary numbers if those are my answers. Which is why we go to synthetic division. Got it? Okay, so let's set it up. By the way, it's in descending order, yes. Am I missing any powers? Gratefully, no. Because if I was, I'd have to put a 0 in, but I'm not. So I've got the power of 3, power of 2, the power of 1, and then the constant. And remember, that first number always comes down. Always. Good? Okay, so what do you guys want to try? Some of you are going, try 1. Okay, we'll try 1. Let me get my, we'll try 1. So 1 times 3. Good, 3. That gives me 7. That gives me 7 when I multiply by the 1. That gives me 0. That gives me 1, and that gives me 3. Did that work? No, because my remainder is 3. It's not 0. That didn't work for me. Okay, nice try, guys. I think I'm going to try my own number. Let's see. You know, I'm not afraid of fractions, because if the fractions don't work, they tell me right away they don't work by basically keeping with fractions. So I'm going to try a fraction. I've got 4 of them. I've got plus and minus 1/3 and plus and minus 2/3. I think I am going to try, let's try the positive 2/3. Hopefully this will work for us. Okay, so 2/3 times 3. Good, that's just 2. This gives me 6. 6 times 2 over 3. Yeah, that is 12 over 3, which is 4. That gives me a -3. -3 times 2/3. Yeah, that gives me a -2. That gives me 0. Yay! So I've got one of my solutions. One of my solutions is x equaling 2/3. That means the factor was x minus 2/3, right? Okay. Now remember, this original polynomial was what degree? Yep, that was a 3rd degree. And you divided it by a 1st degree, which means this is a 2nd degree. And so I am either going to factor it or I'm going to use the quadratic formula on it. One of the two. So let me write it out. We have 3x squared plus 6x minus 3 equaling 0. I'm with you. I'm going to divide everything by 3, make my numbers smaller. So I have x squared plus 2x minus 1 equals 0. Oh dear. That's not going to factor, is it? I'm going to have to use the quadratic formula. All right, so I need to get myself some board space. Okay, so when we divided by 3, we were solving x squared plus 2x minus 1 equals 0. So, quadratic formula time. Opposite of b, plus or minus, b squared, which would be 4, minus 4 times a times c, all over 2a. Okay, so that means x equals -2 plus or minus, let's see, the square root of 4, that's going to be plus 4 here also, so that's going to give me an 8 underneath, isn't it? Over 2. And that square root of 8 can be simplified to 2 square root of 2 over 2, which means -1 plus or minus the square root of 2. Woo! The last two answers involve square roots. See what I mean? Synthetic division is the way to go. So, another answer is x equaling -1 plus square root of 2. And the last answer is x equaling -1 minus square root of 2. You're like, how do you write those as factors? The same way you wrote this one. X, I'd have to add the 1 over to get to the other side and subtract the square root of 2 to bring it to the same side. X, I'd have to add the 1 over and I'd have to add the square root of 2 over. So, here are my 3 solutions. If they want it in factored form, here are my 3 factors. Cool? Okay, hang in there. Got another one for you. Okay, so let's look at this problem. Now I've got a 4th degree polynomial. So I'm not even going to bother trying to factor that. I'm going to find my p's and q's and take it from there. So, looks like for the p's, working with that constant of 8, this is what I have, right? The q's work with the lead coefficient, that's just a 1. So in this particular case, your p over q's, well, looks like they're just the actual values of p because you put all of these over 1, you just get the exact same numbers, don't you? Okay, now, it's in descending order, correct? There are no powers missing, so I don't have to worry about putting zeros in as placeholders. So let's start setting this up. Looks like I have 1, -1, -6, +4, +8. And remember, this first number always comes down. That's how we start. Okay, so we've got 8 possibilities, but I only need 4 solutions, right? Because I get 8 p over q's, including the plus and minus. So what number do you actually want to try? You want to try just one? Okay, we'll try just one. So let me put the 1 in. So 1 times 1, 1, which gives me 0. That's fine. 0 times 1, 0. That gives me negative 6. Negative 6 times 1, negative 6, which gives me negative 2. Negative 2 times 1 is negative 2. Yeah, that's not going to work. So bye-bye positive 1. Agreed? All right. So some of you have another possibility. You want to try negative 1? Some of you want to try 2? Okay, you know, both of those are good possibilities. So let me get myself, get rid of these numbers here. So I can try what you're telling me to try. I think I'm going to try the 2. Let's see how that works. Maybe that'll be a lot nicer for us. Well, there are no fractions to try, so you guys don't have to worry about that, do you? So I'm going to make that guy into a 2. So 1 times 2, 2, which gives me positive 1. Positive 1 times 2, that's 2, which gives me a negative 4. Negative 4 times 2, negative 8, which gives me negative 4. Negative 4 times 2, negative 8. Oh, yay, we got a 0. So good. Okay, now let's notice something. This was a 4th degree, wasn't it? Right? You just found a solution of x equaling 2, which means its factor was x minus 2, right? That means this is a 1st degree, isn't it? So a 4th degree, and you divide it by a 1st degree, that means this thing is that's right, a 3rd degree. So here's the deal. We got to do synthetic division again. But this time on the 3rd degree. Because I want to take this 3rd degree polynomial and knock it down to a 2nd degree. Because when I factor a 2nd degree or use the quadratic formula on a 2nd degree, that's where the square roots or the imaginary numbers will come from. Got it? Okay, so here's the cool thing. I don't have to come up with new p's and q's. I'm going to still use this one right here. I'm still going to use these p's and q's right here. Got it? Okay, so I am just going to rewrite it because I think for most of us this would just be a lot better. And I have the numbers 1, 1, negative 4, and negative 4. And I bring down that first number of 1. And now I have to try whatever. So, what do you guys want to try? Well, you're right. Negative 1 didn't work. Or positive 1 didn't work. Maybe a negative 1 will work. So let's try it. 1 times negative 1 is negative 1. Yeah, that gives me 0. 0 times negative 1, that's 0. That gives me negative 4. Negative 4 times negative 1, that's a positive 4. 0. Oh, good call, you guys. That one worked. Awesome. So now, mind you, right? This was a 3rd degree right here. You just found another solution of x equaling negative 1. So that comes from this factor, which is, that's right, this is a 1st degree, which means this answer is a 2nd degree. 3rd degree divided by a 1st degree gives me that 2nd degree. And this is an x squared plus 0 x's minus 4, second equal to 0. This one you could probably solve in your sleep. You get x squared equals 4, and then you end up with x equaling plus or minus 2, don't you? So, my last 2 answers are a positive 2 again, and a negative 2. So if they want the factors, here are the factors that go with those. Here are your 4 solutions and the 4 factors if they want the factors also. Cool? Okay. You guys have fun with this stuff, and I'll catch